Longest common subsequence. What's the longest hidden pattern two-string share? Longest common subsequence is a pattern mastery 100 staple and a classic in dynamic programming, beloved by Google, Facebook, and top tech interviewers. This problem tests your ability to break down problems into overlapping sub-problems and optimize with DP, a must-have skill for tough interviews and real-world software challenges. Let's break it down. Given two strings, return the length of their longest subsequence, not substring, that appears in both. A subsequence can skip letters, but the order must stay the same. Now, let's assess. Brute force would try all possible subsequences, exponential time. Dynamic programming is the standard and optimal solution here. By building a DP table where each cell dpij represents the length of the LCS for text 1, I, and text 2, j, we can reuse previous results and solve the problem in OM times n, time and space. Here's the plan. Create a DP table of size, len text 1 plus 1, times, len text 2 plus 1, filled with zeros. For each index I in text 1 and j in text 2. If text 1 I minus 1 is equal to text 2 j minus 1, then set dpij to dpi minus 1 j minus 1 plus 1. Else, set dpij to max dpi minus 1 j and dpij minus 1. The answer is in dp minus 1 minus 1. Let's try to implement it using solution 1. Time complexity is OMN. Space complexity is OMN. This solution uses recursion plus memoization. Memoization means remembering answers so we do not redo work. We compare the two strings starting from some positions I and j. If the characters match, we take that match and move both pointers forward. If they do not match, we try two possibilities. We skip a character from the first string, or we skip a character from the second string. Then we take the better result. To avoid recalculating the same I and j situations again and again, we store results in a map. That turns a slow brute force idea into an efficient one. First, we grab the lengths of both strings so we know our boundaries. Then we create a memo map. It acts like a memory bank. Anytime we solve the problem for a specific pair of positions in the two strings, we store that answer. That way we can instantly reuse it later. Next, we define a helper function that answers a very clear question. What is the longest common subsequence between text 1 starting at I, and text 2 starting at j? That means every call is solving a smaller version of the same problem. This is our stopping rule. If either pointer reaches the end of its string, there is nothing left to match. So the answer from that point is 0. This prevents the recursion from running forever. Before doing any more work, we check if we have already solved this exact situation. The key is the pair I and j. If we have seen it before, we return the stored answer immediately. This saves a ton of repeated effort. Here is the main strategy. If the characters match, that is great. We count 1 for that match. And we move forward in both strings. If they do not match, we explore two options. We skip the character in the first string. Or we skip the character in the second string. Then we take whichever path gives us the longer subsequence. Once we compute the best answer for I and j, we save it in memo. That way, if we ever come back to the same pair again, we can instantly return the result. Then we return the computed value to build up the final answer. Finally, we start the whole process from the beginning of both strings. We start at index 0 in the first string and index 0 in the second string. And we return whatever the helper function computes as the final longest common subsequence length. And that's how this algorithm works. It first sets up the string lengths and a memo map to solve subproblems. Then it recursively compares characters and either takes matches or skips from one string while reusing cached results to stay efficient. Efficient, simple, and elegant. Test case check. Longest common subsequence, recursion plus memo. Let's test our function using this input. Text 1 equals ABAT and text 2 equals ACE. These strings represent two sequences, and our goal is to find the longest ordered subsequence that appears in both of them. Here's why the solution works. Our recursive function compares characters at positions I, j. If the characters match, we include that character and move diagonally forward. If they don't match, we explore both possibilities, skipping a character from text 1 or from text 2, and take the better result. And that's exactly what our program outputs. 3. The result matches the expected value, confirming that the memoized recursion is functioning correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using recursion with memoization, efficient and accurate. Let's try to implement it using solution 2. Time complexity is OMN. Space complexity is OMN. This solution uses dynamic programming with a two-dimensional table. The big idea is that for every pair of positions in the two strings, we store the answer to this question. What is the longest common subsequence we can get starting from here? Once we have that table filled, the final answer is sitting at the starting cell. We build the table from the bottom right because each cell depends on future cells. Those future cells come from moving right, down, or diagonally. First, we grab the lengths of both strings. Then we create a two-dimensional table called DP. This table has an extra row and an extra column filled with zeros. That acts like a safety border. In simple terms, DP at I and j represents the best longest common subsequence length we can get starting from position I in the first string and position j in the second string. Now we start filling the table backwards. We fill from the bottom right moving toward the top left. We do this because each cell relies on answers that come from moving forward in the strings. By working backwards, those future answers are already computed and ready to use. This is the core rule. If the characters match, we take that match. So we add one. And we move diagonally, meaning we advance in both strings. If they do not match, we try the best of two options. We skip a character from the first string, which is like moving down. Or we skip a character from the second string, which is like moving right. We store the better result in DP at I and j. Once the table is filled, the answer for the full strings is stored at DP at 0 and 0. That represents starting from the very beginning of both strings. So we return that as the length of the longest common subsequence. And that's how this algorithm works. It first sets up a 2D DP table with extra padding for base cases, then it fills the table backwards using match and skip rules to build up the longest common subsequence length. Efficient, simple, and elegant. Let's test our function using this input. Text1 equals ABC and text2 equals ace. These two strings represent sequences of characters, and we want to find the longest subsequence that appears in both strings in the same order. Here's why the solution works. We fill a 2D DP table starting from the bottom right corner, working our way up to DP00. At each position, I, j, if the characters match, we take 1 plus the diagonal value. If they don't, we take the maximum of skipping a character from either string. And that's exactly what our program outputs. 3. This confirms that the bottom-up DP logic is functioning correctly and matches the expected value. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest common subsequence using a complete DP table, efficient, accurate, and reliable. Longest common subsequence. Let's do a recap. We started by defining the goal. Find the longest sequence of characters that appear in both strings in order, though not necessarily contiguously. It's all about preserving order while skipping unnecessary characters. That's what makes it a subsequence, not a substring. Assess recap. We discussed how brute force would explore every possible combination. Far too slow. Instead, we chose a dynamic programming approach that builds up results from smaller subproblems. By reusing what we've already computed, we reduced an exponential problem down to efficient OM times N time. Structure recap. Our logical plan was to create a DP grid where each cell represents the LCS length for prefixes of the two strings. If the characters match, we extend the sequence. If not, we carry over the best length found so far. The final answer rests in the last cell. Simple and elegant. Implement recap. We implemented the logic cleanly and ran it through LeetCode. The code executed without any issues, efficiently computing the correct subsequence length. Check recap. After running our test cases, we confirmed that the solution produced the right results and passed all validations, a solid confirmation that our DP structure worked perfectly. Closing insight. The key takeaway? Dynamic programming isn't just about memorizing patterns, it's about recognizing overlapping subproblems and using structure to turn complexity into clarity. Master this mindset, and you'll start seeing DP problems as puzzles that naturally fit together.